All right. Hello, everyone. Howdy. Thank you for coming. So this is okay. Well, probably need to plug the HDMI in. There we go. Let's try that again. Howdy, everyone. Welcome to the Secrets of the Universe talk. Today we're going to be talking about formal verification. Real quick, can I just get a show of hands? Who has heard of formal verification? Put your hand down if you've heard it from me. Okay, cool. So we've got a healthy amount of people that don't know a whole lot or have only heard my bad explanations. And that's the position I want to be in because this is going to be the big one. So a little about me, just because this is my last CSG talk, so I'll put it on the record. So I'm Charles Averill, I'm 21 years old. I'm a senior doing CS and physics here. And I am researching source-free formal verification of binary programs with Dr. Hamlin. You'll understand what that means at the end of this talk, hopefully. I'm obviously an officer for the club. I'm applying to PhD programs in formal verification. I'm teaching this compiler design course that you should look at if you want to know about compilers. And my dog's name is Beth, and that's her right there. So let's get right off the bat, and let's talk about the fun stuff, uncertainty and philosophy. Of course, fun things that we all love, right? Just a question. What are some things we know?
Nothing.
Okay, that's one answer. What are some things we think we know?
No thoughts at empty.
Okay.
I have an exam next week.
Okay, that's a good example. Yeah, you have an exam next week.
The Boolean type has two variations, true and false.
Sure, that's something that we think we know. So, yeah, we know simple things, like we know that 0 equals 0. And we know that if you mix red and blue together, you're going to get purple probably, right? And salt is salty, right? These are things that are, you don't even really have to think about them usually, right? They just kind of click in your brain because you're so used to thinking about, or just, processing information like that. And maybe we know some slightly more complicated things, some algebraic relations. So, we can say if, this number x is 0, then x plus some other number y is always going to be y, right? That's something that we think we know, and you'd probably have a hard time coming up with an argument against it, right? Maybe we know the square root of any number squared is that number.
That's not true.
Natural numbers. Formal verification, I'm in natural number land right now. So thank you for being pedantic, but wait a couple slides, please. And so maybe we've even studied some more complicated things about the world we live in. Maybe we know that supply-demand curves are representative of human economic behavior, or we know that cells have programmed death into them when they've got cancer or something. And maybe we know stuff about the curvature of the universe and its effect on how we can observe things. But my question to you is, do we really know any of these things? And if you think that you do, how confident are you? How confident are you that nobody has made a mistake, or that lots of people haven't made the same mistake? If you're not an expert in any of these fields, then you're kind of just relying on, trust. You're trusting that people generally know what they're doing. And at least in the field of cybersecurity, you should not have that instinct. People do not know what they're doing. You should not have that assumption. So we can't, in general, we can't really know things for certain. We can trust people, we can trust things and ideas, but we can't really know anything. Our bodies are here to take in stimuli and respond to them in a way that maximizes our rate of survival. And any kind of higher level intelligence that we've developed to maybe think about math or economics or biology or anything like that, those are things that are, they're side effects of the fact that we are here to, eat and reproduce essentially, biologically. I'm not talking about meaning of life or anything, but biologically, that's what our bodies want us to do. And so as a result of this kind of hard-coded instinct in our bodies, we fall into these things called certainty traps all the time, where we're more certain than we should be about things like software or mathematics, maybe. And these are reasons why like database breaches happen. You're too confident in your security measures, and so you leave them be, or you don't update them frequently or something because you're confident that an attacker won't be able to achieve a database breach.
Charles, your OBS is on the wrong screen.
Wonderful.
Were you certain that it was on the right screen?
I was not, obviously. Just my streaming software. Okay. It's okay, the slides will be posted. Anyways, so yeah, that's why things like database breaches happen. That's why things like physical infrastructure failures happen. Our bridges are collapsing because we didn't expect that much weight to be put on them, or maybe public policy underperforms because we have incorrect assumptions about the way that people act. And so we've got techniques and checks to try and mitigate failures like this, but we still live in this uncertain world, right? So they clearly are not 100% effective. Many things aren't 100% effective, but we want to get as close to 100 as possible, right? And so let's start talking about security first. I'm going to come back and I'm going to explain these quotes later. They're all relevant and somewhat funny, I think. So we've established that we live in this low certainty world, right? But it's not the end. We don't have to live in a low assurance world. So let's talk about high assurance computing. It's this idea that we can make rigorous, mathematically defined, checkable models of software or computing so that we can verify with rigorous mathematics that yes, we made this software correctly, doesn't have any bugs in it, there is no chance that an attacker can exploit some vulnerability. And this has been a topic of research for, 70, 80 years at this point. And the reason you haven't heard about it is because it's really hard. Look at all these cons right here. It's really hard. It takes a long time. It's expensive because you have to pay experts to do it. But you get these amazing pros of, if I have a mathematical model that my software is correct and secure, then I have this supreme security in my software. And I don't have to worry that there's buffer overflows or anything that an attacker is going to exploit. I almost never have to maintain my code unless I'm adding features or something. And so I just get this really high level of trust in my product. For something like a vending machine, you probably don't need to formally verify your vending machine software. But your airplane software, autopilot, or nuclear reactor software, those are things that we really should have a higher bar for. We should not be comfortable with the level of scrutiny that we normally apply to software, right? Do we agree with that? Yeah.
Well, vending machines also have their own financial system just in their own box, and they're connected to very big financial systems all around them, so perhaps everything should be given the maximum scrutiny.
Sure, yeah, I don't know. I was talking about like a coin-operated vending machine. The software in there is, I don't know, but the point is that a vending machine is not high risk. There's not user data in a vending machine. I hope not. If there is, God save us.
You overestimate people.
Yeah. But, I don't know. So let's look at a case study where we have one of these certainty traps in software. And I'll try and keep it as close to standard English as I can. So there's tons of examples of quote-unquote dumb software bugs, things that we should have caught, things that we already know how to catch, and for some reason, for some certainty issue, we didn't catch it. So Heartbleed. In 2014, there was a buffer overflow in some OpenSSL code. OpenSSL is software that deals with secure transmission of data. And so there was a bug in that code that allowed for an enormous amount of information leakage But OpenSSL is used by essentially every computer that's attached to the internet. So there's this vulnerability in all of those billions of computers, and they can all leak information. And suddenly Chase Bank and the United States government, they're all vulnerable to this awful vulnerability that we could have caught because buffer overflows are super trivial to counteract. I don't know. Shell shock, that's another one. We had unjustified trust in these pieces of data that were passing around our terminals. And in the Bash interpreter, which is a very ubiquitous piece of code on just about every Linux system in the world, there was a remote code execution vulnerability. Because we trusted that these environment variables are only coming from other Bash processes, so whatever. But no, an attacker was able to inject data into these environment variables and run arbitrary code. They could run whatever code they want on your machine as long as it's hooked up to the internet. And there's some other vulnerability in your code. But regardless, awful vulnerability. Another big one is Spectre. So CPUs do this thing called speculative execution to try and speed up your code. And we just had an assumption that there's nothing about this thing called speculative execution that's going to reveal any information about the data going through the CPU. That was a false assumption. And researchers found that you were able to find information just by timing CPUs and how frequently they do stuff. And that's real bad. That's awful. These are things that we let ourselves believe, and they had enormous ramifications because of it. Billions of dollars went into fixing these bugs, years of effort. These things shouldn't happen. And one vulnerability I'm going to talk about today, more in depth, just to get the idea across, is Blueborn. So Blueborn is a collection of 8 cross-platform vulnerabilities in the Bluetooth stack. So in your phones, in your laptops, in your desktops, not to mention your headphones and all of those other Bluetooth devices. Just about in every major implementation of Bluetooth, there were bugs in them that would allow for things like remote code execution and data leakage. So this code snippet right here contains one of the Linux vulnerabilities. This one allows for remote code execution. Before I tell you what this function does anyone know what the issue is? And if you've heard me say it before or you know what Blueborn is, don't raise your hand.
We're trusting the link that's being passed into the function.
We're what?
We're trusting the link that is being passed into the function.
This orange thing?
Yes.
No, that's not it. Okay, well why don't I tell you what this function does, and then you can try. So we've got this function, L2cap parse configuration response. And so some background. When you want to connect 2 Bluetooth devices together initially, what do? You pair them, right? We've all paired phones to headphones before and whatnot. And what happens during pairing is that your phone and your headphones are exchanging secret hardware addresses with each other. And these hardware addresses are essentially keys that can unlock capabilities in the other device automatically. That's spooky. So after you've paired your device, what happens when your phone has Bluetooth on and you turn on your headphones?
They pair automatically.
Yes, they pair automatically. Why do they do that? Because any Bluetooth device that has power is going to be always sending and receiving data just out in the air, radio waves, to try and find other Bluetooth devices to connect to. And that's on purpose because they want this seamless integration. But you had better hope that there are no critical security vulnerabilities in all of the code that is external. So all the code that is directly interacting with these free-floating air packages, there better not be any vulnerabilities in those. And there is one. There's one in this one. This is, I think, 1 or 2 layers of code right underneath the hardware that receives a response. So this function is taking in one of these automatic packets that's being sent back and forth. That's RSP. So this device, this Linux device, has taken in a packet from some Bluetooth device, and its goal is, I'm going to look at RSP, I'm going to validate every token of it, I'm going to copy it into this thing called data, and whenever I run out of things to copy into data, which is designated by this len thing right here, I'm going to stop and I'm going to return what I've copied. So knowing that, does anyone have a better idea of what the vulnerability is?
Wouldn't it be just that as long as something gets passed into it and the Bluetooth thing accepts it, it would just copy it into the Bluetooth registry itself, and the person could use that to.
Well, this function is actually validating the package. It's looking at every token. So the vulnerability here is, who can tell me how big the data buffer is? Oh, that's not good. We don't know. This data thing has no correlation to a length. So RSP has a length. These things are tied together. But data, it could be 1 byte long, it could be 1,000,000 bytes long. We don't know.
So it could possibly, I'm going to guess, you can possibly write over other data in the program?
Yes. So you can craft a payload that gets sent into RSP that overwrites out of bounds memory over the edge of the data buffer into memory.
Wait, what's RSP?
RSP is a packet that a Bluetooth device is sending to this Linux machine.
So that's why it has a fixed length.
Yeah, because it's a packet. Yeah. So that's really bad, especially because this can be triggered without any user interaction. That's bad. The reason why is because those secret hardware addresses that I told you about. Well, the Bluetooth people thought they were secret, but actually there was so much unencrypted data in the headers of these packages that you could completely exfiltrate that hardware address just by listening to the device. And remember that these devices are always sending out messages, so surprise, surprise, you can just stand within 30 feet of somebody with this device and you can get their hardware address. Very trivially, it's not even difficult. And so when this vulnerability was released, 5.5 billion devices were at risk. And a year later, there were still 2 billion at risk. That's a whole lot. I don't care if it's more than half that got fixed, still 2 billion devices. And funny thing, so a stack overflow like that one I just showed you is supposed to be mitigated by stack protection techniques like stack canaries, but believe it or not, the standard Linux kernels that you download when you're downloading these boot disks and whatnot are, for some reason, not compiled with stack canaries on by default. Who knows why? I think it's still not the default. You can do it. You can compile a Linux kernel with stack canaries, but it's not the default. That's ridiculous. And I'm sure some of you are thinking, who cares if if my headphone can be hacked and it can run arbitrary code, but you can pair 2 iPhones together. Or you can pair any 2 Bluetooth devices together as long as they have some confirmation technique. So yeah, it's absolutely ridiculous. Things like this shouldn't happen. And so a standard mitigation, good code practices or stack canaries, if they don't work, what is going to work? Formal verification. So let's get into it. The issue with that bug was memory related. We had this issue where we could write out of the bounds of the array. So why don't we use formal verification to build a mathematical model of memory and arrays and reads and writes so that we can prove that there is a way to implement this such that buffer overflows are impossible. So to start out, let's look at what memory is. Well, I'm going to say memory is a function. I'm just going to say that. I'm making this up right now. And if any of you disagrees with me, say it out loud. We can talk about it. But I'm just going to say memory is a function, because you can, if you have some memory state x, or you have some memory state mem, and you give it a number x, some address, it's going to give you the contents of memory at position X. And you can also set the memory, so you call this arbitrary set function, and you give it a memory state, you give it an address, and you give it some data, and it is going to give you a new memory state where you've written some data at position X. So this is an example of a memory state. It's just a list of stuff, bytes, letters, numbers, right? And now we've got these things called arrays. And arrays are this high-level language construct that live on top of memory. So the hardware doesn't implement these arrays, but a language does. C has arrays. And I'm going to say that all an array is the memory state that it's attached to, and the base address of the array, which is right here, this start, and then the length of the array. And there you go. That's a representation of some subsegment of memory that we're going to call an array. Does everyone agree with that? Does anyone have any issues?
I don't like using what is presumably set union between memory state of function and base array address.
Yeah, that's fine. I'm okay with notation issues. I don't know. I wanted something that was parsable. So let's look at how would we access memory in an array. How would we write memory to an array? So I'm going to say, well, if you get the array's memory function, which we said it has, then you can just call that memory function with the base address of the array plus the index you want to read from. And if you want to set the memory of the array, you can just call set this array memory, and then the base address plus the index, and then the data you want to set it to. Raise your hand if you think this is safe. Okay, raise your hand if you think this is unsafe. Okay, good. Who wants to tell me why it's unsafe?
How big is the array we're going to?
How big is the array?
Yeah.
It has this thing called array.size.
How bigger?
Right? Because that's what we said right here. Length, whatever.
Yeah.
That's the length of the array. So why isn't this safe?
There's nothing stopping you from running past the length.
Right. What if index is really big and adding it to the base address gives you some index that's outside the bounds of the array? That would be real bad.
I felt, sorry, never mind.
Okay.
I feel like it would be dependent on what set is specifically doing, because it could include a check for that.
But it doesn't.
Okay.
Because look how we defined it. We just said new memory state with,
Okay.
that's all it does. No, this isn't safe. It's not safe.
Does it have something to do with like word lengths too?
No, don't worry about that. We've just got a list of bytes. That's what memory is, list of bytes. So I'm going to propose that these are safe versions of array access and array write. So what we're going to do is we're going to add the base address of the array to the index, but it's the index mod the array.size. And if you're not familiar with mod, that just basically means if array.size is 10, then this thing is just going to be basically wrapped around over and over until it sits at some number less than 10. So this is always going to be something less than array.size. And we're doing basically the exact same thing here in the set function.
Where the close range?
Don't worry about it. I'm surprised that LaTeX didn't give me an error there. But, yeah, should you believe me? Do you believe me? Do you believe me?
Advance the slide for a bit. It said, can you prove this? Yes.
Okay, but do you believe me?
No.
No, you don't believe me. Do you believe me? Yeah? Okay, we've got mixed opinions. So, okay, let's see what happens. Can we prove this? Can we prove that this thing is safe? I'm going to say, yes, we can. Okay, that's a link to the actual code, but let me pull it up right here. Okay.
I say it's still not safe.
Okay, well, let me do this first, and then maybe we'll talk about it. This is a proof assistant language. This language is going to help me. Can you read this? Is that good? Can people in the back see it? Yeah? Okay. So this is a language where I can express proofs and theorems, and the system is going to tell me with high assurance whether or not the proof matches the theorem. So if I write the theorem 0 equals 1, it's not going to let me write a proof that says 0 equals 1 is a true statement. It's not going to let me, because it's not a true statement, right? So, memory access example. So this is our memory space. It's this memory map thing, which is that function that I said. You give it an address, it's going to give you some byte. And I've also just got a size here. Yeah, so okay, so we've got that, and we've got our read and write functions, which, look, I'll do that. And yeah, so these are the things I implemented, or I said I would implement, right? Okay, and let's just see, what does a 64-bit empty memory space look like? Okay, it looks like a list of bytes, and they're zero initialized, and they've got their indices attached to them. Cool, this is looking good. And we can write to this. So I've got this tiny memory space with 8 bits in it, 8 bytes in it. And I'm going to say write to this memory space at position 7 and put this number in there. And that's the hex number. So this is 16. And look, it gave us a memory state where I had written 16 to byte number 7. Bless you. And we can also read. I can read from position 7. It's going to give me that byte and the index that I asked for. But overflows exist at the binary level, right? You can read out of the bounds because there are no bounds. There's no bounds out here in crazy memory land. And because of modular arithmetic, I mean, you can write to position 333, and it's going to write somewhere in memory. It's not going to be 333 because our RAM size is only 8 bytes, right? But yeah, so we can see, okay, it wrote to position 5, and that's because 333 mod 8 is 5, right? And so I can also read from position 21, which again doesn't exist, but because of modular arithmetic, it's going to give me position 5. And here's our array implementation. It's got the memory space that holds it, and it's got a base address, and it's got a size. That's what we said was an array, right?
Wait, what if you write the value bigger than the byte can hold?
We're only concerned with bytes. Okay. And this is our unsafe array access. This is our unsafe array write. Okay, and so now let's say that we've got some memory, right, on a real computer. And it's got multiple processes running, and there's secret things, and there's public things. And so, someone puts a secret at these 3 bytes in memory. Whatever. It's whatever. I don't know. And then some other programmer comes along, and he puts some data right here at the end of the memory space in his own little array. And then he makes the mistake of reading that subarray that has length 3, but he starts from position 3 on accident. So if you've got position 0, position 1, position 2 of your array, well, if you start at position 3 and start reading, you're going to be reading out of bounds, right? So he accidentally reads out of bounds, and oh no, he has read some secret data. That's no good. And even worse, arguably, he can overwrite it. That's real bad. We shouldn't be allowed to do that. We shouldn't be allowed to mess with other people's secrets, right? So here are our safe implementations of those read and write functions, and we can see that if we've got this original array again, and our original memory space, and he writes an array in there, positions 5, 6, 7, we've still got those secrets at the top. But now he does the same, accidental out of bounds read, but because of our modular stuff, it just gives him stuff that's inside of his array, which is good. Maybe it's not what he wanted, but it's good. We prevented him from reading out of bounds. And we can also prevent him from writing out of bounds. He tried to write all this data. I didn't let him. Wow, so we've prevented read-write access to data outside of the array bounds. But instead of just believing that we did it, why don't we prove that we did it, right? So now we're getting onto this proof stuff. So I'm going to define this mathematical proposition, okay? Just a statement. Could be true, could be false. I'm going to say for any array that you give me, and for any position that you give me, didn't mean to do that. then this proposition says that that position is within the bounds of the array. Right? You give me an array, you give me a position, I'm going to tell you this position is within, it's before the start of the array, and it's after the start of the array, and it's before the end of the array. And so now I'm going to say, oh, look, I've got this theorem, and I'm going to say that if you take our safe array access for any array, for all arrays and for all positions, if you use that array access safe function, then the position you get out of it is going to be within the bounds of the array. And it turned green, which is good, right? We like green. We like green test cases and, yeah. Great, yay, our read is safe. Let's try to do the same thing with the write function. I'm going to say that for every array and for every array that comes after a write, and for every position and for every position that comes out of the edit, and for any data that you want to put into this array, then the position of that data you modified in the edited array is within the bounds of the array. And oh my gosh, won't you believe it? It's going to turn green. Now, who's satisfied? Who believes me? Okay, he believes me. Should you believe me? But then you have to trust him too, don't you? Yeah. So, you should not trust me. You should not trust that system. How do you know that I didn't hard code it to turn green like that? How do you know I didn't add an axiom that just let me assume that, yes, my code works and you can believe me? So the goal of this talk is to convince you, all of you, that this system works, not only that it works, but that there's no way it can't work. Okay? And to do that, we're going to get into lambda calculus. And if that's a scary word, it's okay. This is an extremely simple topic with very complex implications. So just getting the basics down is something anyone can do. So let's get into it.
What an incredible introductory quote.
Thank you. Yeah, let me go back to this quote real quick. Come on. Okay, well, I showed that quote earlier, and it said, hic manebimus optime, which is a quote from a centurion in ancient Rome. The Gauls were sacking the city, and all of the senators wanted to run and leave Rome behind. And that centurion said, hic manebimus optime, which means, here we will remain most excellently. So it's kind of a mantra for doing what you can in an awful situation, which is how I view cybersecurity. All right, we don't have it too good, but we're doing the best we can. So.
I do think there's one unsafe thing about the array that has not yet been demonstrated.
Okay, hold it till the end.
All right.
Yeah. So to start talking about lambda calculus, let's talk about its motivations. And we have to go back about 100 years for that, 130 years. So lambda calculus is this attempt to formalize what it means to do computation. A Turing machine is also the same thing. So you might be somewhat familiar with Turing machines. It's just a mechanical description of what a computer is, and we have this idea that Turing machines can do anything that is computable. Well, lambda calculus is a mathematical approach to defining what is computable. And so we can reason about it much more effectively, in my opinion. So lambda calculus and Turing machines came about during a very rough time in mathematics. We had finally formalized everything with set theory, and we were very proud of ourselves. And then disaster struck, and we found paradoxes in the fundamental assumptions of set theory. And that's a big deal, because if you have paradoxes in your assumptions, then how do you know that anything that is derived from those assumptions is true? You don't. So there was this effort to really formalize what was going on, come up with some consistent set of mathematics that could talk about what is computable, and that's how lambda calculus was born. We wanted to make sense of what it means. What does it mean to do computation? What does it mean to represent an equation, some symbolic equation, or define, figure out the truth value of a statement? And so these four guys, that's Alan Turing. You probably recognize him. This is Alonzo Church, one of the creators of the lambda calculus, or the primary one. This is David Hilbert, who led the program in mathematics to figure out where all of our mismatched assumptions were. And then that is Haskell Curry, all the way on the left.
Younger Ford.
Hmm?
Younger Ford.
What?
No.
Okay. So let's get right into it. Let's implement the lambda calculus. There it is. That was easy, but probably not very clear. I mean, can any of you read that? Or tell me what it means? Probably not. So let's put it in English. In lambda calculus, we have these things called expressions. And before I go any further, I want you to forget everything you know about mathematics. I want you to just know that we are inventing stuff right now, and nothing has any more meaning than we ascribe to it. So don't come at me and say this is a math expression and it has to follow algebra rules. It's not that. It's our own thing, and we're making it up right now. So I'm going to say that an expression can be one of three things. It can be a variable name, whatever that is. It can be a function that takes in a single argument and returns some other expression. And we also call these abstractions. And so, that just means function, the lambda. That's a variable name. That's the expression it simplifies to. And then the third thing an expression could be is just an application of two other expressions. And so to actually do computation with this system, we actually only need one rule. So whenever we're applying two expressions, if the left one is an abstraction, take the right one, find that variable, that v right here, and replace all the occurrences of that variable with this thing on the right. And I know that wasn't very clear, so let's look at Abstractivate. So he's got this thing in him called an expressive box, right? It's got some expression in it. It could be math, it could be your grandmother. It doesn't matter. It's whatever. We haven't put any meaning to this yet. And he's saying, can you please give me something? My name for it is going to be x. I don't know what you're going to give me. I'm going to call it x. And so we can see in his expressive box, he's got these x's in there. And that's what this lambda calculus expression is signifying. So it's saying, give me some x, and I'll give you something back. And so I give him something. It's whatever. It's alpha plus beta to the epsilon. It could be whatever. And he's going to say, wow, thanks. I'll give you back whatever's in my expressive box, but anywhere I had an x, I'm going to plug in that thing you gave me. So we had x's in there, and now we've got this thing I gave him. And that's what this application looks like right here. So we're going to get this thing back. We give him that, and he's going to give us this thing. Is that is that clear? Does anyone have any issues before we go on? So, Abstractivate wants something, wants you to give him something. His name for it is x. And so you see he's got some x's in his expressive box. Maybe he doesn't. He doesn't even have to. But if you give it something to him, he's going to replace all of the x's with the thing you gave him, and then he's going to give you this whole thing back. Okay. So, now that we know the fundamentals of what lambda calculus is, what can it do? Well, I think I mentioned earlier that lambda calculus is Turing complete. It can do all of the computations, period. It can represent numbers. And if that doesn't look like a number to you, I don't know, it is, because I called it one. We're defining things right now. We can do whatever we want, right? So I'm going to say this thing is 0. And I'm going to say that there's this thing called successor, and it gives you whatever number you give it plus 1. And the way you can count numbers is however many f's you see in the expression, that's the number minus 1. So 0 has 1 f in it, 1 has 2 f's in it. Bam. We've got a representation of numbers. We can represent booleans. which are actually very interesting in the untyped lambda calculus because they're just two argument functions where true returns the first thing you give it and false returns the second thing you give it. Do we see that? And so that makes implementing if statements really easy, because if you've got some condition and then you've got two branches P and Q, then you just apply P and Q to the condition. And because the condition is a two-argument function, if the condition is true, it's going to give you P, and if the condition is false, it's going to give you Q, because that's the second thing that came to it. Pretty nifty. And then we've got this monstrosity down here called the Y combinator, and that's what allows us to do arbitrary loops in lambda calculus. So recursion, for loops, whatever, you can do it. Mess around with it if you'd like to. But there's some issues with lambda calculus. For one, there are no data types. So we've got numbers and booleans, but everything's just a function. So I could use a number as a boolean. Even worse, I could use a boolean as a number. Like things that don't make sense in our understanding of what, true false values and integers, like those two things can't really collide. And the worst thing is it's a legal expression. You can do that. It's legal. Another big issue is that there's non-terminating expressions in this language. So you can infinite loop in this language. And because I use this syntax to represent that loop, that rule, the one computation rule, right? That's what I said. If you've got an abstraction, you've got a thing, just return the expression, replace, whatever, right? But this double down arrow is saying, I promise you that if you give me this, I'm going to give you this. But if you've got an infinite loop, it's never going to turn into something. It's just always going to keep transforming. And so we've broken our mathematical promise. And mathematicians really don't like when you do that. So we don't want to make them angry. We don't want to come up with a system of computation that allows for something like that. So how are we going to solve this? Any ideas? One simple concept. Well, one cool concept. I wouldn't call it simple. Types. So, as with lots of things in computer science, types are the answer. And just by adding types to the lambda calculus, we can fix some of our big issues. But we're going to lose some stuff and we're going to gain some stuff. But let's give it a chance. So, this is our new semantics and syntax for the language. We definitely used to have that, yeah. We used to have that. It can be a variable, it can be an application. We have an abstraction again, but we've got this thing right here. And what this is saying is, this is an abstraction, and this variable that you're going to give me has to have some kind of type t. And the function gets to define. So if the function says, my input is going to be an integer, you can't give it a boolean. It's a compile time error. It's not going to let you. It's just not a legal expression in this language.
What's the first thing?
I'll get to that in a second. So we said these were expressions, but now we've added this new kind of object called a type. And a type can be one of two things. It can be a unit, which is, again, a thing we made up that I called unit. Or it can be this arrow type. And this arrow type is going to represent functions. So it's saying if you give me a T1, I'm going to give you a T2. Input type, output type. And you can string, because these are types, you can string them along recursively. You can make really, really long types. So this thing right here, this open close parentheses, according to this new rule that I added, I said the type of that thing is unit. I said that. This isn't a theorem, I'm not proving anything, I'm defining. The type of this thing is unit, just because I said so. And I'm also going to say that if you give me an abstraction, the type of that abstraction is the input type, right there, arrow, the type of the thing in there. Right? That's what we said. Right? You give me a T1, I'm going to give you whatever the type of my E is, which is a T2 in this case. And finally, if you have an application of two expressions, the thing on the left better be a function from some type T1 to some type T2. Doesn't matter what type it is, but it better be a function on the left. Otherwise, it's not a legal expression. And the thing on the right better be a T1. So let's say that E1 is an integer to integer function. You give me an integer, I give you an integer. But E2 is a bool. You're trying to apply a bool to an integer to integer function. Not allowed. This thing has to be an int in that case. Okay? Are we comfortable? I know that picked up speed a little bit, so interrupt me now if you need. Yeah.
Right now we only have units and functions.
That's right. We're going to add stuff. Is everyone else good? Great. So here, some basic examples. This is a function. It takes in an integer and it returns that integer plus 5. And I'm assuming we have some integer type. Don't think too hard about that one. Or I can return. You give me a string, I'll add hello world to it. Or if you give me two functions that take an int and return ints, f and g, I'm going to compose those two functions. Sure, cool. Okay, so we've covered some lambda calculus. Let's take a little detour to a fun little puzzle that will come in handy later. It's called type inhabitation. So first thing first, we're going to add a new type, and we're going to call it void. And void is a very special thing because there is no expression that has type void. Period. Doesn't exist because I said so, right? We're inventing stuff. And we know that, so, according to rule 2, we said this thing has type unit. And so we're going to say that the unit type is inhabited by the value, open close parentheses. Right? That's what inhabitation means. A type is inhabited if it's got an expression that has that type. So we can show that the type unit arrow unit is inhabited because we can make this value right here. This is a function that takes in a unit called x, and it just returns that x. Right? Unit to unit is inhabited. Do we agree? Okay. So we said void is uninhabited because there's no expression of type void. We said unit is inhabited, and we said that unit to unit is inhabited. So can someone tell me, is the type void to unit inhabited?
Well, what's it going to take in?
Well, just tell me. Yes or no? Is this thing inhabited? I want to know what people think.
Yeah.
You say yes. Does anyone say no?
I'll say it.
You say no. Okay.
Let's fight. Let's fight.
Okay, sure.
Why is it inhabited?
Because
Better question. Give me an expression with this type. That's how you'll tell me why it's inhabited. So what expression has type void to unit?
a function that just returns unit doesn't take in anything.
A function has to take in something.
Then take in a void type.
Bingo. Contrary to popular belief, this type is inhabited. I'm going to say lambda x colon void dot open close parentheses. So I'm saying if you gave me a void, I would give you a unit. You can never actually call this function because we said there aren't any voids, right? But you can write that, and it's a legal expression. What about, oops. What about this type? Pretend you didn't see that. Is this one inhabited?
Sure.
Why?
Return the void that's passed in.
Great. Yep. If you gave me a void, I would give you that void back. That's technically a void-to-void function. You can never call it, but it's there. What about this one, unit to void?
No.
No? No? Yes?
It implies the existence of something that inhabits the void type, and because void is uninhabited, there cannot be such a thing.
So yes or no?
No, you cannot.
Okay. We say no. You're right. There is no type. There's no expression that has this type.
Wait, why is that?
Well, okay. If you wanna disagree, then give me a lambda expression that has this type. Write me a function that takes in a unit and returns a void. You can't. That's the point.
Sir, it almost seems like to me that some Boolean concepts of Boolean are inside.
Interesting. Hold on to that thought. Let's add some more types just for fun. Let's say that you can have a pair type. And a pair is just two expressions stuck together. Not applied, but they're in some new data structure we just invented. And we call these product types because we represent, so if this is the expression, then this is how we write the type. And we use that multiplication symbol, so we call this a product type. And we have these things called sum types. I'm going to call them constructed types because you build them out of other types. And the way you can write an expression of type T1 plus T2 is you use this thing called con1 or con2, short for constructor. So if you use constructor 1, then this E has to have the type T1. And if you use constructor 2, this E has to have type T2. Okay? Just because I said so. So we can't make a pair that has we can't have a pair that is void times something, or something times void. We can't do that because you'd have to give it an expression that has the type void, and we said that's not allowed. But can we make a sum type that has the type unit plus void?
Yes.
Shout it out.
Yes.
No, shout out the expression. There you go. Yes. So you can use con1. You can't use con2 because you can't give it a void. But yeah, there we go. That has type unit plus void. Great thinking. Just for fun, try showing that that's inhabited. It is. So before I go any further, this is the critical point where I need you to ask any questions that you have. Or if you're uncertain about anything I've said, it is critical that you ask for clarification now. Otherwise, you're not going to believe me when I get to the end.
Can you go up to the con again?
Yeah.
So from the syntax, con1 and con2 don't tell us what E is a type of?
Well, you're going to give it E, and E is going to have some type. And if you're using con1, that type has to be, we've added, I've implicitly added typing rules that say E has to have the type T1.
And then con2 has type T2.
Yeah.
Can we review the syntax for lambda calculus?
I mean, we don't really need to, but it's not critical, but
All right.
it's yeah.
How does a void function work?
If you gave me a void, I would give you that void back.
Oh, that's what it's saying.
You can't give it a void.
Can you explain on the cons how the sum differs from like a function type?
Because a function says, if you give me this, I'm going to give you this. The sum type is going to say, I'm going to give you an object, and it's going to be wrapped in a constructor that determines whether it's a T1 or a T2. Okay? Any other?
So you're saying if you give it the unit can't vanish into thin air. You can't.
Sure, that's the way to look at it. It's wrapped up, yeah.
Is it like a union?
A union? Sort of, yeah. Hold on to that thought.
What's the point of the product types?
You like lists, right?
Okay.
You can use pairs to build lists recursively.
So is that just use, like the calling it a product type is just used to define it, just that it holds some object of type?
I mean, calling it a product type is just, that's whatever we called it. But yeah, this is implementing pairs as you know them in like Python, tuple. Yeah.
Or Struxon's type languages like C.
Sure, yeah. Okay, any others? All right, I'm going to go on. We're in the home stretch now. This is where it starts getting crazy. So we had all those rules about what valid expressions have as their types, right? These are those rules that we said. And the whole point of these rules is that we can look at a lambda calculus program, and without running it, we can statically check whether or not that thing is well typed, which means that you can't put a Boolean into a number. You can't put a number into a Boolean, vice versa, whatever. Everything goes where it's supposed to, right? And let's look at just a very simple type checker that I wrote. Can everyone see that? This is a type checker for the simply typed lambda calculus. It's only got arrows, lambdas, and units and variables. So it doesn't have the products or sums or whatever, but it's got the basics. And this is the entire thing. all it's doing is saying, if you gave me this thing called gamma, which is essentially that type of operator that I was using, and you give me a store which just maps variable names to their values, then if you finally give me some expression, I'm going to tell you whether, I'm going to tell you what type that thing has. So if you give me a unit, that open close parentheses, I'm going to tell you that thing has type unit. That makes sense. If you give me a variable, then I'm going to look into my type of thing. I'm going to get the type of that variable, and I'm just going to return that. So the type of the variable is the type of the thing, that the variable contains. And if you have a lambda, a function in abstraction, and its input type is tau, and it has this term inside called t, expression, same thing, then I'm going to say this thing has type arrow of that input type plus the type of whatever the term inside it has. That one was a little much. Do we get that? Arrow type of whatever the input is, whatever input type the lambda function defined, and then the right part of the arrow is just going to be the type of the inside of the function, that e on the inside of the function. Okay? Okay. Finally, if you have an application, I'm going to say this better be an arrow on the left, and whatever is on the right, something called LT3, then the input type of that arrow has to be the same thing as the type of the thing on the right. Because that's what we said, right? If you've got an application, this thing has to be, the thing on the left has to be a function, and the thing on the right has to be the proper input type of that function, right? So that's what I'm saying here. And then if that's true, then I'll give you the type of the thing inside the lambda. Okay, that's the entire type checker. There's like one extra line of code in another file that just says if the type of this term is the expected type. And that's the entire type checker. How many lines of code is that? 8 through 31. That's 23 lines of code. That's pretty darn good. I mean, like 30% of it is like, printing errors. That's a pretty good line count, in my opinion. Very small. That's a good thing, and we'll see why. So now that we've got all these ideas about lambda calculus, types, and inhabitation, I want to assemble them now into what is, in my opinion, the most beautiful mathematical theory ever discovered. It's called the Curry-Howard isomorphism, and it wraps all the things that we've been talking about into one amazing, very simple statement, which is that types are theorems, mathematical theorems, propositions, statements, and programs are proofs of theorems. Let that sit for a second. Types are theorems, and programs are proofs. If you've taken discrete math, you've written proofs before. You were writing programs, and you didn't know it. You were reading types, and you were writing programs. Why is that? Well, why did we do type inhabitation? I said it was a puzzle, but I did it for a reason. So we said that unit was inhabited, void was not inhabited, void, times void, uninhabited, da-da-da. Yeah, we said all these things, right? So it's clicking, right? You recognize this order of false and trues because you've written truth tables before, assuming you're a computer science student. Oh my goodness. Hang on, let's look at that. So all I did was I took all the units and I replaced them with this T, and I took all the voids and I replaced them with F. I took the stars and I replaced them with the conjunction operator, and I took the pluses and I replaced them with the disjunction operator. And then arrows stayed the same, which is very cool. So let's think about that. Yeah, true is true. Yeah, obviously. False is false. False and false. That's false. True and true is true. Right? True and false is false. Right? We're comfortable with this. We know truth tables. And then these, I've found that people are less comfortable with. But if you think about them, this is saying false implies false. So you're saying, if I'm assuming false is true, then false is true. Yeah, that's kind of trivial. It doesn't make any sense to write a theorem that assumes a false statement as an input, right? But you can. False does not imply true. If you assume, no, sorry, backwards. Yes, false does imply true, because true is already true. It's easy to prove that true is true, right? True implies false, nope. You can't prove a false statement. No amount of true statements is going to prove a false statement. And then true obviously implies true. Implies that true is true.
What does STLC stand for?
Simply typed lambda calculus, which is what we just implemented. So I want you to think about that. Together, in the past, 30 minutes, 45 minutes, we defined, didn't derive, we defined a language that natively encodes philosophical ideas of theorems and proofs within the structure of the language, within its types and its expressions. Not only that, but it can be pretty trivially type checked. I showed you the type checker. It fit in 23 lines of code with error checking. And its semantics are simple enough that they fit on one presentation slide. That means, think about those three very important key components. So if we very, very carefully write code, and we very, very carefully verify it with mathematicians, that means that we can create a high assurance, automated proof checker. We can use those three components that we just came up with, that you said that you understood. It's your fault. I said interrupt me if you don't understand. So if you don't understand, it's not on me anymore. We define a system that you understand that will allow us to state theorems, write proofs for those theorems, and then have an incredibly high assurance that those proofs are true. That's a really big deal. Is it hitting you that that's a big deal? I see some yeses. I see some blank stares. Maybe you're still thinking about it. And so this is where Coq comes in. That proof checker that I showed you right at the beginning. Coq is an automated theorem proving system. It contains a programming language in it called Gallina, as well as another proof language that's technically called Coq. And it's essentially an implementation of the Curry-Howard isomorphism as I just explained it to you. It binds the concepts of types and theorems and programs and proofs into a comprehensive, cohesive lambda calculus called the calculus of inductive constructions that allows for high assurance proof checking. It does this, it gives us this high assurance because it has an extremely small trusted computing base. The trusted computing base is the section of code that is not proven to be correct. So the Coq compiler, 99% of it is proven to be correct by itself. It uses its own proof checking capabilities to verify that all the functions that make up the compiler are correct. And the only thing that is not verified by itself is that type checker that I just showed you. And that thing has been looked at by thousands of mathematicians for the past 40 years. 60 years, actually. They planned this out for 30 years before they wrote a line of code. They were planning this system out in the 60s and 70s, and the first commit in the Git repo is in 1996. That's how long they thought about this before they ever put pen to paper. And now, they've got this thing called MetaCoq, which is a formalization of Coq in Coq, so you can verify the type checker. Isn't that crazy? That's wild.
The above proposition is occasionally useful.
This one?
It's a joke.
Oh, okay. So, someone said something. Question?
Sorry, I guess for me, I'm not really following at all, but it still seems like it might fall, run into the whole Goodell's.
Why? Tell me why. Metacoq proves that Coq is correct. Yeah,
But Metacog cannot prove that Coq is consistent?
yeah, it did.
Wait, how?
It has a consistent set of axioms that don't contradict one another.
But Coq cannot prove that there may not be some later state in there that makes the whole rest of the system inconsistent. If it can prove
No,
that,
you can prove that adding an axiom is not breaking cohesion.
but that by
That's how they do it. People have debates about adding axioms to this system, and if you can prove that it doesn't break cohesion, then you can add it in.
But if you can prove,
Yeah.
but it's not a guarantee.
Well, they're not going to let you put it in there unless you have a proof that it's not breaking cohesion.
So it doesn't violate Cox's completeness theorem. It doesn't violate Gödel's second completeness theorem.
The second incompleteness theorem is the one that says that no mathematical system can represent all true statements, right?
That would be the first one.
What's the second one?
I've heard it.
Never mind. Let's talk about this after. Sorry. Question.
Okay, so they have the base, and that's verified by mathematicians.
Yes.
They re-implemented the base in car, and then they verified that using.
Metacoq is like a completely separate project. I wouldn't say that it's part of the core concept of the system, but essentially Metacoq is formalizing what it means for the type checker to be correct, and then Metacoq verifies that with proofs using Coq. So it's bootstrapping. So it's going back down to that original implementation of the type checker. So that's where the trust comes in. The only part of this system that you have to trust is verified by thousands of mathematicians for decades, and I think the number that gets quoted often is that it is 50 lines of code. 50. I am pretty comfortable trusting that. Yeah? Are you? Okay. It's up for you to decide. Anyways, so that was the main matter of this talk, and I'm just going to get into some extra stuff that's a little neat to talk about. So let's talk about the calculus of inductive constructions a little bit. So that's the lambda calculus variant that Coq relies on, and it combines three very essential additions to the type system that I showed you that provide the expressiveness necessary to state all of the theorems that we're interested in. So parametric polymorphism basically adds functions that take in a type and return a term, return an expression. So you've probably written those before in Java or Python. Python? Does Python have template functions?
Yes, now it does.
Okay. Well, you've probably written something with templates before, where a function, like an array sorting or a list sorting algorithm, you don't want to write an int list sorting algorithm because then you can't use it for your string list, right? So you'd write one sorting algorithm that works for any kind of list as long as you give it a comparison function, right? That's parametric polymorphism. And again, that allows us to express generic data structures. And dependent types are a very exotic addition that you are most likely not familiar with because not many languages have them. These are functions that take in a term and return a type. That's kind of wacky. So you can specify in the type of a list that list has 5 items in it, or that every item in that list is even. It's weird, but it's very essential because that gives us the ability to represent the outputs of functions in our theorems. And we need that because we're proving that the outputs of functions are correct, right? We're proving that some manipulation of data does what we think it does. So we need to have some way to reason about the output of functions. So the output of the function is this term that's affecting the type, which is that theorem, right? Due to the isomorphism. Also, it gives us the for all operator. So I can say, for all numbers, this property is true. You wouldn't be able to do that without dependent types.
How does it actually give you the for all? What's the reason?
Because I don't want to give you a wrong explanation. Let me look this up after. This slide is the shakiest part of the presentation because if you look up why these three things are necessary for Coq to function, there's lots of conflicting viewpoints about why each of them matter, which is really, really annoying. And all the people that know for sure never write it down. They all just know it. So you have to ask them, and they didn't respond by the time that this presentation happened.
You asked them.
I asked on the Coq forum about this, and I got half a response. But anyways, the last one is type constructors. These are functions that take in a type and return a type. This is like a template class, okay? And that's necessary to avoid some very interesting paradoxes I won't get into about, like, what is the type of type? I don't know. You have to add these things called universes, and it's like a whole thing, and I'm also somewhat shaky on that because it's not even something the average formal verifier has to deal with. But it also gives us the exists operator. There exists a natural number such that this property is true. This is the lambda cube. This is the lambda calculus we implemented. If you add parametric polymorphism, you get this thing. If you add dependent types, you get this thing. And if you add type constructors, you get this thing. And so you can combine these in different ways, and it makes a cube. And so if you've written OCaml's in this area. There's also many conflicting viewpoints about where OCaml goes in this. Pretty sure Haskell is up here. OCaml is close to it. And Coq implements all three, so it's up on the top right. Just for fun, let me show you this thing I wrote.
Oh, yeah.
I wrote a renderer in OCaml.
Is this the one you showed us today?
Yeah. Yeah. It's not very bright, but it's pretty cool. Little lambda cube 3D model in my renderer. Cool.
10 MB GIF file. 10 MB GIF file, what?
10 megabyte GIF file? Oh, because it's like 1,000 by 1,000 pixels and it's 60 frames a second, and I had to optimize it pretty hard. Anyways, so last thing I want to do. I know this has been a very long talk, but I just want to walk through a proof. Very, very simple proofs in this system. So let's break down what all this says. This one says there's this thing called nat, short for natural numbers. We're making it up. We're making up a thing called natural numbers. It can be one of two things. It can be this O, which is short for origin, or it can be this S, which is short for successor. So it can be the successor of another natural number. Cool? I mean, think of your intuition about what a natural number is and tell me that this isn't a valid representation. You can't, because that's like the canonical way to do it. This theorem says, okay, so let's break it down. Not even just this theorem says. When I use this theorem keyword, I'm saying I'm going to state this property called add0r. Okay, I'm just going to state it. And I'm going to say that for every natural number n, if you add 0 to it, you get the same number back. I'm going to phrase it that way. I'm just going to say it. And Coq says, nuh-uh. Says, I don't believe you. So you have to go down here and you have to say proof. I'm going to write a proof now. I'm going to prove to you that this thing works. And you're going to do induction on n, you're going to do stuff, and I'll show you in a second the internal representation, but this one, it was easier. So this one says that for every Boolean value, which is true or false, that Boolean value and true is just the original Boolean value. I mean, that's a true statement, right? And I proved it pretty easily. But so here's, I stated this in language that we'll understand because we derived it. So I'm going to say, I think this type is inhabited. This type, which says for all B, B and true is B. That's a type, remember? Types are theorems. I'm going to say, I think this type is inhabited. And, that's how you would write it. Pretty sure. Again, type constructors are weird. Dependent types are weird. And Coq says, I don't believe you. Not for a second. So I'll say, okay, I'll show you that this theorem is true. I'll show you it's inhabited by building an object that has that type. So I'll say function takes in a Boolean value, does a case analysis of this Boolean value. If the value is false, then it's going to replace b with false, and that's the and function. It's going to say by the property of reflexivity, which just says that every object is equal to itself. By the property of reflexivity, these two things with reflexivity make a true statement. It's going to say if b is true, same thing, but with replacing true in there. So that's a proof. That's the representation. That's the type and habitation way to think about writing proofs. And it's also very fun to think about it the backwards way, where programs are proofs of type and habitation too. It's kind of wacky, kind of funky. That's it. That's the whole thing. So, is everyone convinced? Okay, better question, is anyone not convinced? Did I say anything that your brain is screaming out, this is wrong, this doesn't work, this is inconsistent?
It's a small thing and it has to do with the erasing that I mentioned earlier.
Uh-huh. Go for it.
There are some formats I know for strings, there's a specific encoding format, Unicode, in which even though we can write specific bits and that's a valid write, you can write bits such that it can create invalid characters that Unicode cannot parse.
I didn't say anything about that in my correctness specification.
What I'm thinking is that you can have an array that is safe and that you can easily read and write to it.
Yeah.
But it becomes unsafe because it can contaminate otherwise safe code.
No, because it only writes within the bounds of the array. And I proved that.
The contamination would come about because I would suppose it would be weakness in the receiving expression, but essentially if it's expecting a Unicode encoded array. Yeah,
but that's like a completely different correctness specification. You have a different idea about what it means for your array writes to be safe than what my correctness specification was. I proved my correctness specification. I encourage you to come up with a version that is safe in your manner. All right. Anyone else have any inconsistencies? Do you see why this is like a sleeping beast kind of? Like this is waiting for people to just get at it. Like only in the past 10 years has Coq become usable as a proof and program language enough to actually, prove big, large pieces of code as correct and whatnot. Before then, it was a hassle, is what I'm told. So.
Require a different architecture to prove something that was written in C or Python?
Nope, because you can formalize the semantics of the C language. Better yet, you can formalize the semantics of binary code, because there are semantics. They're really weird, but you can do them. And that's actually what my research with Dr. Hamlin is over. We have formalized the semantics of many ISAs, and now we want to use this system to prove the correctness of parts of the C runtime library that don't have any source code. So it's not even like, I can verify that the source code is correct, and then I can verify that the compiler is correct. You can't, because there's no source code. So if you want it to be known as correct, you have to prove that the binary program is correct.
Wait, there's no source code?
Yeah, memset. There's no source code for memset. It's just assembly. That's the one I'm proving right now. It's a real pain in my ass. I've been working on it for like 7 months. No proof yet. I'm pretty sure it's true, but convincing a machine-checked proof system of something is very, very difficult.
If you prove it false, you get a Nobel Prize. You get a Turing Award, whatever it's called.
No, I would get a patch to the Linux kernel, glibc. That would be neat. Huh? No. DARPA is funding our research to develop this system. So I get money from there.
You work for the government?
Yeah. Yep. Okay. Any other questions?
If we're interested in learning more about this, what are some ways we can do that?
I am so glad you asked. There's this wonderful textbook. But it's written like a blog post, and it will teach you how Coq works. It'll teach you how to write proofs. It will introduce you to the fundamentals of induction if you're not familiar. It really assumes that you have almost no prior knowledge, which is wonderful. So it'll teach you these things. This is volume 1.
Show an example of what the book looks like.
Good idea.
Showing you right now.
Well, no, I mean,
Scroll back.
He already showed you some code in the book, actually.
yeah. So it's going to introduce concepts like induction. It's going to say, yeah, we can prove this thing. I'll give you some example proofs, and I'll show you some proofs that are wrong, and I'll show you why they're wrong, and then, let's write a proper proof. And then it'll give you some exercises that are fun, and they turn green, and that gives you a little dopamine boost, and it's better than crack almost. So when I first was learning Coq, it was the winter break last year, and Dr. Hamlin had told me, if you want to join the research lab, read through this textbook, do the exercises and whatnot. And I don't know, I was like, okay, yeah, I can do that. And within a chapter, I was going through it, and I had, spending hours trying to figure these out. I'm very proud to say that I've posted my solutions to these, and I have a few solutions that aren't on the internet yet. I'm the only one, so not to brag. So yeah, excellent textbook. Probably the best I've ever read. Easy to read. It'll give you a comprehensive overview of the system. Absolutely go look at this. Software Foundations, online, free. Coq is free. You can download it. This will tell you how to set it up even. So, Windows, Linux, whatever. Question?
Okay, so just to make sure I understand, so you give it a type that has certain properties, and then you make an assertion about the type, and then you give a proof, and it verifies it.
You don't give it no. So your assertion is a type. Theorems are types. Same exact thing, just with different names. And your proof is a program that the type checker is going to look at, and it's going to say, yep, okay, this thing has the type of the theorem you just stated, which means that type is inhabited, which because of the isomorphism means that theorem is true.
Okay, so you have a list of properties, and you're making sure that something with those properties exists?
Yes, essentially, yeah. A proof is showing that there is an object of that type, a legal lambda calculus object.
Oh, okay.
When do we get to the secrets of the universe part?
That was the secrets of the universe, dude. I just told you something crazy about the fundamental nature of logic. The ideas of doing computation are isomorphic to the ideas of mathematical propositions and proofs. That's wild. That's the secret of the universe.
Well, yeah. No one else knows about this?
I mean, if you look at the percentage of the human race that knows it, it's pretty low. So now you're part of the exclusive club that knows why the Curry-Howard isomorphism works. And I will say that I definitely skipped over some bits that a pedantic person would, pick out. So I'll give you another resource. Dr. Hamlin's APL slides. I am not afraid to say that this course, APL, was the best organized course, best course I've ever taken, also best organized course I've ever taken. The slides are wonderful. They are much more pedantic than I was.
Can you show us?
Sure. Let's look at simply typed, this is a parametric polymorphism.